Lecture 4.2, Order, Disorder, and Entropy. The first law of thermo does not distinguish between heating and working. They are on the same footing. Or changing internal energy. And that's what Joule taught us. However, the second law of thermo, and this is the concept of entropy, does distinguish between both of these. So what I want to do here is that I want to share an image with you. And here's what I want you to do. So I'm going to share this image captures the core ideas. And so what I want you to think about is that I want you to consider 3 phases of a material, which I'm going to pick as ice, water, and water vapor. So here is the image. And so what I want you to think about here is that in this situation, I'm going to come in here and I'm going to lightly color these just to show you that there are 2 extremes. There's this highly ordered system, which has sort of like a lattice, it has a lattice structure. And so it's very organized. This one here is very unorganized. And so you can tell that this guy up here is going to be ice. This one down here is going to be water vapor. So now let's start thinking about this. So what I'm seeing here is that I'm going to be moving downwards. So in other words, when I move down, I am going in this direction. Okay, so this is the downwards direction. So if I focus in the downwards direction, what do I see here? Well, for starters here, I see that I have up where I start with, if I have a highly ordered arrangement. And clearly, this is not a random system. But as you move down, what you start to see here is that I get to a state that's highly disordered. Oops, I think I spelled that wrong. Right, that's a highly disordered arrangement. Therefore, this is a very random system. And the way I try to visualize this process here is that you could imagine that you clean your room on Sunday. The natural progression of your room, if you don't put any energy into cleaning it up, it gets messier and messier if you don't do anything. So in essence, when I'm thinking about the left side, here's what I'm going to be writing. So if I look at the left side, I imagine that I have ice crystals, and if I just let it sit, there's an intermittent region here, and I would say that this right here is water. So I go from ice crystals to water vapor. And so what we see here is if I start to summarize this thing, I'm going to say that there. So if I look at what's the most probable thing that's going to happen is that if I have a glass of ice and this ice, starts radiating heat, or heat from the room comes in, what you're seeing here is that there is an increase in randomness as you go down. And so there's a scientific term for this, and I'll mention it for the first time here. And the scientific term here is that you're seeing that I'm going from a highly organized system to a highly disordered system. So, so let me not talk about that scientific term yet, but I just want to be really, really clear that I start with, let me back up a little bit because I'm getting ahead of myself. So I start with ice crystals, which is highly ordered. Then I go to water, which is somewhat in between. And then I finally go to water vapor. And water vapor is highly disordered. And again, the example that I said, but I think it's worth talking about here, is that I have, so as an example, if I have a cup of ice and nothing interferes, just a cup of ice all by itself, what happens? It naturally melts into water. And then it evaporates. So if I had a front running movie, a forward running movie, nothing would look out of order. So then, following our process before, a front word running movie would show a physical process. Not a problem. And again, I said this already, but I think we should write it here. So to get a sense here, here's my analogy that I talked about is, so I said, if you clean your bedroom on Sunday, then that means you start off on Sunday with a highly ordered bedroom. All the clothes are put away. There's nothing on the floor. You know, all the dishes are out. They're in the kitchen now. But as the days progress, the bedroom becomes messy, right? It becomes messy, which then becomes a highly disordered state. So if you don't put any energy into your room, it naturally goes that way. So then what I'm going to say here, a scientific term for this randomness, so a measure of the amount of randomness is called entropy. It's a new concept, but it's a scientific term. So in this case, if you look at the bedroom, you start on Sunday, by the time you get to the middle of the week, then we say then you've gone from an ordered to a disordered state. We then say that entropy increases when disorder increases. So the more disorder, the higher the entropy. So if you have more disorder, that implies that you have a higher entropy. If you have less disorder, then you have a lower entropy. So then what we say here, that the most probable situation when ice melts or your bedroom naturally gets messy so the most probable situation when ice melts or your bedroom naturally gets messy is the normal way of physics processes. So now if I look at the right side, let's look at the right side this time. So if I come back up here, here's my right. So what do I have here? Well, you see that I already have a highly disordered arrangement. So what I'm going to say here is that now I have a highly disordered arrangement. And the only reason why I'm rewriting it is that so that it comes across, right? We say that this is a very random process here. But now what we're going to do is that this time we're going in this direction. So as I move up, so here, this is as one moves upwards, and this other one was as one moves downwards. What we see here is that when we get up to here, we now have a highly ordered arrangement. So when I look at this thing, this guy has high high randomness. This guy has low randomness. So if I look at my right side, what am I actually seeing here? Well, I'm going to see this. So here's my right side. So in the right side, we then have the situation that goes like this. There is a decrease in randomness. As one moves upwards. So in this situation, we now have water vapor in the air. Okay? We have water vapor in the air. So this is highly disordered. So then all by itself, the water vapor does what? It now collects into water. And then it now forms a more ordered state. So then it would form ice crystals all by itself. In other words, go into a highly ordered state. So clearly that's a problem because it is not possible for water vapor all by itself to organize itself back into ice crystals. It can't do it. So right away, what do we say here? A backwards running movie, oops, shows an unphysical possibility. Again, if we go to the analogy of the bedroom, think how ridiculous this is. Your messy bedroom, right, which is a highly disordered state, will not clean itself. Right? Wouldn't it be nice if you could have your bedroom all clean itself? Yeah. So unrealistic, of course. So you can't go from a highly disordered state to a highly ordered state all by itself. That's what entropy is really telling us, that that's not possible. So then if I continue to keep looking at this, this is clearly a decrease in randomness, implies a decrease in entropy. So a decrease in entropy is not possible globally, as we'll talk about here. So what is the probability of the room actually cleaning itself? What? We say that this is most improbable. Situation that your bedroom or water vapor getting back into ice crystals cleans itself all by itself. It doesn't work that way. So clearly, we have to answer the question, which I think we've already have, but let's be a little bit more careful in how we write things. Then we have to ask the question, what is the distinction between ordered versus disordered states? So we need to introduce a new scientific concept called entropy. which is a state variable. It's a state variable which is a measurable physical property. And so here we go. So we define entropy by the letter S, but just like momentum, we can't talk about momentum without as the change in momentum. You can't talk about velocity without the change of velocity. So just like entropy, we can only talk about the change in entropy. That's the only thing that's physical, which is written as delta S. S by itself is meaningless. Only changes in entropy make any sense. So now we've already said it, but we should write it here. We can then say that entropy is defined as a measure of randomness or disorder of a system. It's a little bit more technical than that. It's essentially what is the most probable state that you're going to find the system in. This concept was first introduced somewhere around the middle of the 1800s by a guy named Rudolf Clausius. I believe he was German, but he was the guy that actually came up with this idea. That was an idea that was missing. So let's try to interpret this and then go to some examples here. Okay, so now let's interpret this. So what do I mean by that? Systems all by themselves, and that's really crucial, all by themselves, always move from a low to a high disordered state. And so what you're finding here is that now when we look at the entropy of the universe, that is an absolute positive quantity. So there's got to be two more situations. Systems all by themselves that start at equilibrium will stay at equilibrium. So in other words, we could say that systems that start and end in a high disordered state That's the definition of equilibrium. Then this tells us here is that the entropy of the universe does not change. It stays at zero. So what is the probability of moving from a state of equilibrium to the next state of equilibrium? It's the highest possible probability. And then we say that systems all by themselves never globally, and you'll see what I mean here in a little bit, move from a high to a low disordered state. And in this case, we say that the entropy of the universe, where you have a decrease, that this guy is not possible. So what we want to do here is that we want to start looking at a couple of things. So the first thing that I would do is that I want to see if I can actually get a really good picture in your mind to actually get a sense of what I want you to see here. So what I'm going to do here is that I'm going to set up my applet, which I've set it up now. And so let's go into these details now. So I'm going to say, let's be a bit more technical. And this is really the most important of the statements. It says that entropy there's no H here. Entropy, remember it's a state variable, is a measure of the probability that a macroscopic state will occur, and this is super important, spontaneously. Okay, this is the important part, spontaneously. So this is really the definition of entropy right here. We haven't even said we haven't even written down the second law here, but we are actually going through this right now. So what I'm going to do here is that I'm going to deal with PhET. So we're going to use PhET, the states of matter applet. And what are we looking at? Which state is most probable for an isolated system? And look what I'm going to say again. Remember, it must occur simultaneous, or maybe not simultaneous, but spontaneously. That's the important thing. So let's go to the applet. So here's the applet. So when I'm looking at the applet, what do I see here? I want to start off with the gas state. So if I start off with the gas state, this is my gas state right there. Now, as I look at this gas state, I'm going to ask, what is the most probable situation? Is the most probable situation of the gas, is it something like this? So here's my most probable. So I pause this, and then I say, what is the most probable state right now, the next split second? It has to be this highly disordered state. So now, if I do the exact same thing, I say, what is the probability if I start right here, and then all of a sudden, it goes into a solid like that? What is the probability? It's extremely, extremely low. So then I want to, let's go back into my notes, and let's write some stuff down. So what I'm looking at is that I'm looking at this right here, and then the next split second, it's going to do this, and then I'm going to go and put this image right here. Now let me go get the solid image. Actually, I have to move this over here. And then here's the image of the solid. So you can clearly see that this is a highly disordered state, right? So if I look at this thing, this is highly disordered. This is highly disordered. This is highly disordered, and this has a very low disorder. So now what happens? It has to occur spontaneously. Remember, when I say this word right here, I really mean that it's happening spontaneously. It's happening spontaneously. So then, here we go. This is clearly the most probable outcome. This is clearly the least probable outcome. So what we say here is that, so if I go from here to here, this first system here, we say that a system that starts in equilibrium will stay in equilibrium all by itself. It's just the most probable situation. So in this case, when we look at the change in entropy, we say that the change in entropy of the universe, well, it's zero. I started at a high disordered state, and I continued at a high disordered state. But not the case on the right here. And we could say here is that a system will not organize all by itself into a much highly ordered state. So in this case, we then say that the universe, the entropy of the universe, that is definitely negative. But however, we could go for something like this here. Now let's go back to the applet. What if it wasn't spontaneously? So what if I start here? Okay, here we go. So what I'm going to do here is that if I look at this this solid here, note that I can add heat, right? I could add heat. No. Let's not do that. I'm going to make it easier. So let's not add heat, but it does apply for adding heat. So if I look at this thing, let's say that this is ice. What I know about ice here is that after a period of time, it melts and it becomes like this over time. And then over time, then evaporation occurs. And now I have this situation. So we can see how ice can go to water, can go to water vapor all by itself. But now, so if I did a frontwards running movie, that would look normal, right? So in this case here, let's go back and write this before we move on so you can see where this other one is coming from. So in this case, we can then say that over a period of time, ice can melt into water and then evaporate into water vapor. So I think I still have an image of the solid here. So let me, if I could put this in. So, yep, there's my solid. I have my gas right here. Now I just got to go get my liquid. So if I now go and I look at this guy here, it's going to look something like this here. Let me go grab this. And then here's my liquid. So now I look at this guy right here. Okay. So what I'm seeing here is that I have the following situation. I go this direction, I go that direction, and what I see here is that I start off at a low entropy. Then I get to a mid value entropy. And then I get to a high entropy value. So what you're seeing here is that I'm going from a low. So when I look at the change in entropy for the universe, I'm going to have the entropy of the water vapor minus the entropy of the ice, and that quantity is then going to be positive, right? That is positive change in entropy. Now, what's highly is going like this. So now let's say that I start with water vapor. This is the example that we've been talking about. Over time, is this water vapor all by itself going to go as a liquid? No, that is decreasing entropy. And then all of a sudden, the liquid water now becomes ice, which is even a lower entropy state. So when I'm looking at this, then we could come back and we could start asking the exact same thing. Over time, water vapor will never organize itself such that this happens. I believe I got this guy. Actually, I have the liquid right here. Let me go get the gas. And let me go get the solid. But when you're looking, the progression that we're looking at is we're looking something like this here. That as I move in this direction like this, you're seeing I'm going from a high entropy to a mid-value entropy all the way to a low entropy. So when you're looking at this change in entropy then says that I'm going to have the low entropy of the ice minus the high entropy of the water vapor. Why? Water vapor has more disorder. Ice has less disorder, and you can see here that this guy is negative. That does not happen. So then, if I now apply the same type of thinking to two thermally interacting systems, so now if we apply this to two, thermally interacting systems, we then start the exact same way. So what do? I have two systems. Let's say that this is them right here. And so they're insulated. And then I'm dividing them out like this. So when I'm seeing here, I could imagine that this is my hot, and then this is my cold. Now, what's going to be really important here is that you got to remember the red marbles. So this represents the red marbles. This represents, oh, I should have colored that green. Well, I'm going to call them blue marbles. And so what you're seeing here is that this guy has a hot temperature. This one has a cold temperature. So what we know here is that heat transfer moves in this direction right there. So this is the transfer of heat. So what you're seeing here in this picture, that initially this is a highly ordered system. And why? Because you see here is that you have them, these are isolated. Somebody had to pick each of these little gas particles and put them in the hot and then put them in the cold. So therefore, that's highly the case here. So therefore, this tells us that this is low entropy. But now, these guys are going to interact. So as they interact, what are they doing here? They now reach thermal equilibrium. In other words, on this side and on this side here, what you're going to find here is that these guys are going to reach eventually the same temperature. So what we're saying here is that it's now, we then say that the final state is highly disordered. Why? There is now a mixture of gases similar to the red and blue marbles. So in this case, this is a high entropy case. The natural progression of the system is to transfer from low entropy to high entropy. That the heat, it has to do that. Now, if we continue along this same line, we will never see this happen. So what I'm going to do here is that I'm going to take my container here, and I'm just going to copy them. And then I'm going to adjust them. So I'm going to come and put them in here. So what I'm going to do this time is that now I'm going to erase these a little bit. So that means here, so I need to get rid of this. I need to get rid of this. And the other thing that I got to do here is that I need to modify this a little bit. So I want to look at this guy here. So now you could see that I have the separation still of the hotness here. And then what we're going to do here is that now, again, look what we do here. We initially start off with a highly ordered system because they were able to isolate the hot and the cold. So now if I start to look at the gases mixing, what are the probabilities that the hot side gets even hotter? The cold side gets even colder. So this situation says that this is the hotter, more than hot, right? This started off at hot, but now it gets hotter. And this started off as cold, but now the left side got colder. This final state is even more ordered. That means that the faster gas molecules continue to go to the hotter one, the slower gas molecules continued going to the colder one. Than before, which then implies here is that the hot gas got hotter while the cold gas got colder. What is the probability of that? Well, in this case, this is even a lower entropy. So therefore, this represents a decrease in entropy, not an increase. So in this case up here, we clearly see that the entropy is positive. In this situation, we see that the entropy, change in entropy, is negative. So now, let's go write down the second law. Okay, this is the second law of thermodynamics. So the change in entropy, delta S, of an isolated system never decreases. The change in entropy either increases until the system reaches equilibrium. Or if the system begins in equilibrium, it will stay at equilibrium. And the way we write entropy is we then say that the entropy of the universe, there's a lot of ways to write it, but officially it's written as dq over t. We don't really care about this. This can either be greater or can be equal to zero. This is the second law of thermodynamics. And I gave you a lot of images, conceptual image, but we're not really calculating the entropy so much because we're going to do something else. So I don't want to write too much because this topic is so vast and so incredibly interesting. So if I was to rewrite this thing to try to make it clear, I could then say that one can think of entropy as nature's tax. If a system is left unchecked, for example, your bedroom, right? If you start off with a clean bedroom, over time, the disorder increases. That's the natural states of system. This is also the case of humans. And again, there's a lot of things that I could say right here, but here's the way I would think about it. Humans, and I can also just say organisms. I didn't say humans were organisms. I know some people would get upset for me saying that, but either way, humans interact with its surroundings um, how do I say this? They interact with their surroundings via entropy, via heat, right? So they interact with their surroundings. Oh, I know what they interact with their surroundings by expelling uh, entropy, I guess that's the right way to say that, via heat. Okay, via heat. And when they do that, in order to gain local order and reduce local entropy. Okay, this is a mouthful right here, and I'm kind of struggling to how to actually say this. So I said that this is also the case with humans. We interact with our surroundings, and I say by expelling entropy. Like when you take a breath and you blow it out, you are really increasing the overall disorder, because when you have a breath inside your lungs, that is definitely a low order, and when you blow it out or when you're sweating, you're actually increasing entropy in the environment. But we have to do that in order to gain local order and reduce our local entropy. So our ability to do this, right? So I think this is the deep one here. Let's see if you can grapple with this one. So global, and by the way, I have not been saying global, I've been saying the universe. So the global disorder increases. You increase the overall entropy. But for humans, the ability to locally control / reduce entropy is literally a matter of life and death. Well, that's a deep one. You can think about that quite a bit here. So now let's just finish this here. So in summary, I could then say isolated systems evolve such that, one, order turns into disorder, randomness. And then sometimes you'll hear people say chaos. Two, isolated systems never spontaneously, and remember that word spontaneously is super important. Isolated systems never spontaneously generate order out of randomness. If you open up a can of soda and all the CO2 jumps out, what are the chances of the CO2 all getting back together in that can? They can't generate that kind of order. The system does not know about order slash randomness, but rather, um, but rather, how do I say that? But rather, the, oh gosh, the system does not know. Oh, but rather the vastly more states corresponding to randomness. In other words, it's really telling me that here that entropy must increase. Boy, that was, I don't know how smooth that came across. So this is the end of the physics of the second law. And the reason why is that the vast majority of the people who take this course do not go into physics. The vast majority of the people, so now I'm going to say that now we head towards engineering slash chemistry, thermodynamics. Because the vast majority of the people do that. I would love to get into the microscopic behavior and the parameter omega to actually talk about that, because that's really the true definition of entropy.